Hi, this is a demonstration of using the R package ham to analyze the NHSN SIR or standardized infection rate data from the Center for Disease Control and Prevention, the CDC, using their data from their NHSN department, which is, I think, National Health Safety Network. And so they track infection rates from over 30,000 hospitals throughout the U.S. and U.S. territories on infections such as CAUTIs, CLABSIs, VAEs, and surgical site infections, or SSIs. So I'm going to go ahead and start. We have RStudio open. Again, my R package ham is an R package, so RStudio is a graphic user interface to show that. I'm going to go through a little bit of background about R if you're new to R, and we'll just begin with the packages, and it's a way for a user to create a set of commands for a variety of reasons and to create different functions to perform different tasks. And mine is used for healthcare analysis methods, and that's where the acronym HAM comes from. So I'm going to first library HAM. I'm going to call or load HAM so that I can use its functions. We're going to look at different HAI types. Those are hospital-acquired infections, sometimes also referred to as incidents if it's a broader description of data. And for the definitions of our outcomes, or for the different types of infections, we have central line associated bloodstream infections, commonly referred to as CLABSIs. We'll also look at catheter-associated urinary tract infections, CAUTIs. We'll look at ventilator-associated events, which are VAEs. And lastly, we'll look at surgical site infections, SSIs, and these are for, I'm using the most commonly found surgical procedures within these hospitals, and those are from colon surgeries in adults 18 and over. And I believe this whole data set is for patients 18 and over. Okay, so what I'm going to first do is I'm going to load data. I have data sets with each of the infection types, and in those are the data from 2016 through 2024. And I also have the models that I ran, and I used 2016 through 2024 because that has the most complete data, but also the expected part in the SIR, the standardized infection rate, is based off of regression models that use the 2015 baseline data. It changed after 2022. So the most recent baseline set of data that was used to create the prediction formulas or the regression formulas happens that new baseline is 2022. So that and that's just being applied in this past year. So I can use the data between 2016 and 2024 because it's going to all be based on that same 2015 baseline. So now we've loaded our data. I'm going to check actually I think I need to run it. Okay, so on the right you can see within the environment, on the top right corner, we have our data sets. We have two types. We have one that reads as the infection, for example, CAUTI at the top line, and then immediately below that we have CAUTI_DF. And that data frame or that data set includes the 4 non-U.S. states, which is Washington, D.C., and Guam, Puerto Rico, and the U.S. Virgin Islands. So it includes non-states and states within, whenever you see data ending in that underscore DF, that would indicate that it would be the full data, not just the 50 U.S. states, which are not denoted with that underscore DF. For example, CAUTI has just the 50 states. Okay, so we're going to go down to our analyses. We're going to do two different studies. The first we're going to look at is on CLABSIs, and we're going to answer a couple questions. The first question being, was there an impact of COVID-19 on CLABSI? Was there an improvement in 2022? These are just kind of broad general questions, but we want to see if starting in 2020, if there was a change in the SIR, and did we see another difference in 2022? In the study, the variable or predictor of U.S. statehood is an intervention, or we're going to call it an intervention. Is there something unique to these 50 states that may have impacted CLABSI differently for the U.S. states versus the non-states? Washington, D.C. is within the U.S., but just for the sake of this demonstration, we're going to consider it a non-state, even though the District of Columbia is within the United States. And so we're going to look at 50 states versus 4 non-states, D.C., Guam, Puerto Rico, and the Virgin Islands. We'll do both types of models that we can do in HAM within our causal models. The first is differences in differences. And the second type of causal model that we'll do is interrupted time series. And these are very helpful for program evaluations. Say if you're implementing an evidence-based program or project or practice, then the logic behind of using these causal models is that we put a lot of effort into creating those programs, and our evidence-based practices are based off research, which is focused on internal and external validity. And the purpose is we want to make sure we're doing our studies correctly, but we also want to make sure that we can interpret how well these studies can be applied to future data, or how well can we spread these projects that might help our hospital setting, how well those can spread to additional settings. And so we have a lot of good, careful practices, and when we develop these evidence-based programs or projects or practices. And now we want to be able to assess whether what I found useful in the literature that worked in one setting, is it now working in my setting? And so how we can do that is with causal models. For example, differences in differences helps because we have a control group and we have a pre and post test at the same time. And when we have more complex questions about trends over time, we can use interrupted time series to help answer those. So it makes sense that we're going to assess an evidence-based practice or program with causal models that take advantage of the research design that we applied to that, to our program evaluation, but also to how those evidence-based programs were developed. So we're going to kind of complete that loop of good research practices by using these causal models that are developed for specific types of research design. And by doing so, we get a cleaner and more accurate set of results with greater precision. So let's now move on to the model code. And this is using the ham package. And so if you're new to R, what we're going to do is we're going to create an object. And that object name is DM1CL. D is D for differences and differences. I'm actually going to do both an ITS and a DID model. I'm just going to use D though for the first letter. DM for differences and differences model. It's our first one, and it's for CLABSIs. And so in the assess function, we're going to first do our model formula. Our outcome is the SIR, and it's regressed on all of our routine variables for that model. So within ham, it's going to create a set of variables that represent our main variables for the analysis. One of them being a differences and differences variable, DID. Like interrupted time series, our DID study, our model, to get that differences and differences effect, it creates an interaction between our intervention variable, which is in this data set, the US date, and our time variable, which is year. And so the interaction between the two gives us the DID variable. And so that interaction is generated within the assess function. So this very second row, those are specific to differences and differences study. The next row down, in that third row of code, represents our arguments for our ITS model. So ITS of 2, that indicates that it's two groups. We have an intervention and control group. I forgot to mention that for that DID argument, 2 means something different. It means it has 2 time points, like a pre and a post. The other option is many, but we're not going to do that in this analysis. We're going to look at a pre and post, so we have 2 time points, whereas for ITS, that 2 refers to the number of groups, which are our intervention and our control group. And we have interruptions, similar to a treatment period. Treatment equals 5 means that it's the 5th year of this data from 2016 through 2024. So that treatment at time point 5 means that it's a treatment for that year of 2020. We can do more than one time point. We can have as many interruptions as the data permits, and so that's generally 3 units of time per time period. And this interrupted time series is also referred to as segmented regression. So imagine we have a long straight trend line, and that's how we generally think about trends. But that may not always make sense. And so what we can do with interrupted time series is break up that single trend line into segments. And we can do it at interruptions. And those are for, in our data, it'll be the 5th year and the 7th year between 2016 and 2024. And so we're going to allow our trend lines to break, or for us to test between those 2 segments, that we would test between our current segment and our previous segment. And within the Shadish, Cook and Campbell book, there's a section on interrupted time series that describes more about that. I would highly recommend that reading if you want to use interrupted time series more. But so that's how we're going to set up the data. There is one last argument that I selected true for, and that's new data. So if you prefer using, say, if you're not an R user and you prefer using something like SPSS or SAS, or stata. What you can do, if you still wanted to get these kinds of variables generated for you, you can just run this highlighted code and then save the data. Within the DM1CL object, there's going to be, if you select new data equals true, you're going to find data with all of those variables. The differences data is not too hard to replicate on your own. It's just the interaction. You just want to make sure to do that interaction. But for whenever you do the interrupted time series, you get a lot more variables because you're now, instead of working with one trend line, you're working with segments. So you may get a lot of variables back in return. So I would definitely recommend, if you just wanted to get that data and work with your favorite statistical software, just run this code. Make sure to select new data equals true, and then save that data and export it to whatever your favorite statistical software is. But if you want to continue using this package and you do like using R, then there's a lot more you can do with that, and I'll review these in these following sections. Okay, so I'm going to put in there, I'll put a link to where you can get my data files, which have the models that I've already run. I'm just going to highlight and run this code just so you can just to show you. But I'll put that in my GitHub page, and so it's going to have the data and all of these different models. So if you want to try out these commands, such as the summary, which will just give you the model results, you can run and highlight that here. We're just going to scroll up a little bit. Okay, so we can see that we have 4 coefficients. The top one is our intercept. The bottom 3 are the variables that were created through the assess function. The main one that we want to focus on is the DID. That's our interaction, and it shows that value is negative 0.23908. It's significant at a alpha level of 0.05, so that p-value is less than 0.05. And what I have included in the ham package are interpretations. So we can look at the interpretation for this model. I ran that command. And to run a command, in RStudio, you press Control and Enter. If you're working directly in R, not this GUI that I have open through RStudio, but if you run R directly, then you would just press Control and R to run that line of code. So we can see that, I'm going to scroll up a little bit. So here's the command, interpret, and it produces interpretations. It tells you what kind of model you're looking at, DID, and then it begins to give you information and a description on the intercept. That first predictor, post all, and we can read that it's the change in the control group's SR value in the second time period. There was a significant increase for the control group at time 2, and that coefficient is 0.259. We see that below that is our int.var, or the intervention variable, and it's the difference between the intervention and control group at the baseline period, which is time 1. The intervention group had a significant decrease in the mean SIR value compared to the control group, and that's negative 0.345. And now we're at our main variable, which is for our DID variable, and DID estimates the average treatment effect on the treated group. This interaction represents the difference in the trend differences for the intervention and control groups. So it would be intervention time 2 minus intervention time 1, and that change in the trend is then subtracted by the control group's time 2 value minus their the control group's time 1 value, and that comes out to negative 2.39. So if you're not familiar with the differences in differences study and you're in healthcare, you've probably heard of the study by John Snow on cholera back in 1854. He found a significant difference in the mortality rate for two different, I think there were two different boroughs or two different water districts that were supplied water from the Thames River. One came from a contaminated part of the river, and the other came from an uncontaminated part that was upstream. So their water was fresher. And so he looked at before and after data for I think there were two control groups where the data was combined. It may be two intervention groups, but I'm pretty sure there were two water sources that made up the control group. And what he did was he looked at the before and after for the mortality ratio, and then from water that came from the uncontaminated part of the Thames River, and compared it with the other group. So what he did find was that there was an improvement in the mortality rate in that uncontaminated part of the river. So he was able to successfully identify that that cholera was a waterborne infection. So he used that same control group in pre-test, post-test to identify that source, and we're using that same type of model in differences. And so that's what the DID value, or that variable, represents. It's if we're looking at changes between pre and post, between a control group and an intervention group, that gives us what essentially is a difference in trends. So that's what the DID estimate is. Okay, so now that we have our interpretations, we may want to graph these. We may want to know which part of the coefficients had the biggest impact on our outcome. In other words, which was the more important variable. So we'll create a variable importance graph. I'm just going to highlight this set of code. X11 is a graphing window. I have parameter preferences that I'm going to use to graph this plot better, and then that last line of code, it's going to plot the importance calculation for that model. So I'm going to run the model now. I'm just going to actually use this. I'm going to click on the run. You can also use, you can click on the run icon at the top. Okay, so we have our plot graphed. Okay, so for my importance plots, they'll print the level of importance, and that's a partial chi-square statistic. You can read about it more in the documentation, but with a larger statistic, it becomes more important. And so we line up our variables in ascending order for importance. So we have our most important predictor at the bottom, and when it's in red, or whatever color you want to choose, it shows up significant in that color. All three of these are red, so that would indicate that these are statistically significant variables at the 0.05 level. We have our p-values on the right side. All three of these are significant, but when you look at which single variable or coefficient had the biggest impact in what our predicted scores would look like. It would be our intervention variable. Since this is an interaction, we're most focused on what that interaction variable is, but I just wanted to point that out because we can use it. Assess will do just regular ordinary least squares or linear regression models as well as logistic models, and you can use that in those analyses as well. Okay, so now that we've looked at importance, we're going to look at the model. We're going to summarize the model results with the graph. I can just do that in a very basic way with just running plot, typing in the regression model name DM1CL, and then in the next space, separated by a comma, we would put the type of regression model we did, and that's in quotes DID. And so by default, it's going to create the intervention group with the blue line and our control group with the red line. And so that we can see that in that dashed vertical line that's in gray, that's in the center, that's going down in the center, that indicates when our treatment occurred. So it's not really a treatment, but our intervention happened at the 5th year, so everything to the right would be from that 5th year on, and everything to the left would be from the first 4 years of data, starting in 2016. And so we can see a pre and post trend for our two groups, our intervention group in blue and our control group in red. We can see for the most part it appears that our intervention group stayed, the CLABSI SIR stayed about the same. And then when we look at our control group, which are the 4 non-US states that are in our data, we see that it increased overall. So we have to remember that we have 4 years to the left of that dashed gray line and 5 years to the right. So just in the broadest sense of before and after, this is what that trend looks like for both groups. Okay, so I'm going to go back. I'm actually going to use that. I'm going to plot the importance, and it's going to go back to this open plot device or a graph. And now we're going to produce a graph with more detail. For example, I'm going to include confidence intervals with that conf.int argument. I'm going to add a legend, change the line width. I'm going to add the counterfactual line. This is the what could have happened had our intervention group if they would have had that same trend that our control group had. So without a treatment, this is potentially what that trend could look like over time for our intervention group. We're going to change the size of the legend. We're going to add in legend names. We have a main title. We're changing our x and y-axis limits. Changing our points for our different axes. We're also changing the label size of our labels, changing the label name, changing the size of the main title. We're going to add coefficients in there so we can see what was in our regression table. We're going to put it into our graph, change the text size in our graphs. I'm going to change the transparency of those confidence bands. We have confidence intervals checked off So we're going to have confidence bands, and we're going to make those more transparent or less transparent. A value of 0.2 is means less transparency than, say, a value of 0.5. And I'm going to move around some of those, the coefficient text, the values. I'm going to move the one for DID, for our DID coefficient. I'm going to move it around so that we can see the, we can read it better. Okay, so I'm going to run this code. Okay, so now we have this new graph created, and we can see what all of these different regression values represent. Intercept is where our control group begins. Post all is the change in the intercept, or the pre and post change. How much more did the SIR increase in the post period for our control group? And that value is 0.26, and it's significant. INT var, I believe that was the most important predictor. Yeah, it was. We see that INT var is at the bottom of the importance plot, indicating that it's the most important. That is negative 0.35. So there's the our U.S. states had a lower SIR by about 0.35 points before 2020, and 2020 is that vertical dashed line. It's hard to think of it as a treatment or an intervention, but that would be what those arguments define, that we're looking at a pre and post based off of the year of 2020. And so it's important to remember that we have 50 states, 50 rows of data for each year versus 4 for our control group. So most of that data is dependent on where that baseline period started. Okay, so, and then we go finally to the DID coefficient, and that equals negative 0.24. So, and that's significant. So when we look at the trend for our control group, which is in red, and the trend for our intervention group, which is in blue, the difference, if you were to subtract this trend for the for our intervention group, or the 50 U.S. states, and we were to subtract the trend for our 4 non-U.S. states that are in red, that value would be negative 0.24, which would indicate that, as we can see here, for the most part, our 50 states, they stayed about the same. When you consider this is 9 years of data with pre and post around the year 2020. So this stayed at level, but it did increase by about maybe 2 points, and we know that because when we look at the post-all value at 0.26, so 0.26 gives us a difference of 2 between 0.24 and 0.26, so this probably increased about 2 points. This difference between these two would represent what that DID is. Our control group went up 0.26, and the difference between going up 0.26 and going up by only 0.02 is that 0.24. And so that's what this result reflects. But we also see this counterfactual line. And had this also increased by 0.26, it would follow that same trend as that dashed blue line. And we can see in the legend on the top left, that counterfactual is the what could have been had the 50 states followed the same type of trend that our non-US states had. If they did, they would have, the SIR levels would have aligned with this dashed blue line. And so it didn't, it stayed level for the most part. And then that's the difference between, precisely the difference between this dashed blue line and the solid blue line is 0.24 SRI points lower for that solid blue line. So that would be how we get our result. And you can graph all of this with the ham package. And you can produce a graph like this that gives you the values for the coefficients. And actually, I do have options to show arrows so that, for example, there would be an arrow pointing down from this dashed blue line to the solid blue line to remind you that that negative 0.24 with the arrow pointing down would indicate that it's a decrease from what could have been. Okay, so let's go ahead and close these windows for now. Okay, so we've done that first study. Now we're going to look at, we've done the first studies, the first question of the first study. Now we're going to look a little bit more deeply into what happened at 2022. So in the code that I ran for that first model, the DM1CL, I did the differences in differences study and the interrupted time series. I coded for both at the same time, so we already have that run. So we're just going to run the summary command for our model results, and you can see that there's a lot more output with this summary. The two that we're usually focused on most would be variables or coefficients that indicate changes in the trends and intercepts. What's nice about interrupted time series is that you get values for both the intercept as well as the trend or the slope. So within a line we have an intercept and a slope. The intercept's helpful because it tells us what's the type of impact that your program immediately has. Is it a shift right away, or is it a gradual change in the trend? In other words, what kind of effect do we expect to see? So if you're doing hospital programs, depending on your administrators, they may want something that shifts a change right away, or maybe with some outcomes that are more difficult to change. Maybe we don't expect an immediate shift, but maybe we're happy with the gradual change. Maybe there's a program that we're willing to invest in long term to help improve our outcomes. And if you're lucky, you get an immediate shift followed by gradual improvements over time. But we don't often get that. So interrupted time series, more than other models, provides us a way to see that. What kind of change do we have, and what kind of immediate shift do we have or change do we have, and is there a gradual change over time? And we can do that because with interrupted time series, because it gives us values for our intercept as well as our trend or our slope. So the variables, I'm going to highlight the rows that give us that intercept and slope. And for that first interruption, we would be most interested in that IXP5 variable, and that means the intervention groups or intercept at that time point 5, or 2020. The fifth year is 2020. And that TXIP, when you see a T, that refers to a trend, And when you see the I in there as well, that means our intervention group. And so we can see that with these two variables, we have a significant shift in the level with IXP5, a significant shift in the intercept, and we see a trend that increases, but more at a marginally significant level. So you can see, but with the results, we can see that for the U.S. states, their CLABSI rates increased and the trend was pointing upwards. So that might be surprising, but that's what the data reflects for that 2020 and 2021 time period. So we're going to go down to the next intercept and slope. And those are in those bottom two rows for the variables IXP, for the interventions intercept, and the TXIP is the trend for that intervention TXI. The T would be trend and the I would be for the intervention. And so we can see that we have negative coefficients for both. That means that rate went down after starting in 2022, and then we can also see that trend is pointing down as well. So that's that would be good news for the 50 states. Okay, so we see that in the summary, but it may be easier just to read the interpretations of that. So if I run this code interpret with the model number, the $sign at ITS, that's going to give me the ITS model interpretations. Okay, and so we get these results here. I give descriptive interpretation for each variable, for each coefficient. Let me just go down to the bottom one. I'm not going to read them all, but I just want to show you the bottom set of code for that TXIP 7 variable. That's the trend for the intervention group at that 7th year, which is 2022. TXIP is negative 0.511, and significant. This is the difference in both groups' slope changes since the prior intervention, pre-slopes compared to post-slopes. For example, both have pre-intervention slopes of, and this is a hypothetical just to explain how to interpret that in general. For example, both have pre-intervention slopes of 2. In this hypothetical example, the control group slope remained the same, therefore the first intervention slope is 0, and the intervention group slope increased by 2. Then TXIP1 equals 2, and that's 2 minus 0. And that's how we would generally calculate each of these different values when we're looking at these TXIP variables. We would look at the, similar to the difference in differences, we'd look at that trend between, for our intervention group, we're looking at the trend in slopes for our intervention group minus the trend in slopes for our control group. And so that's what TXIP7 indicates. And I do have these summary values, and these sum up what that trend is for each of those different time periods. We don't have the trend for the baseline, but we have a trend for our 2 interruptions at 2020, which would be summary 1, and then our trend for summary 2. For this, we'll start with summary 1. For this intervention period 1, the results show that the intervention group's non-significant shift in SIR post-intervention was 0.027. The control group's non-significant shift in SIR post-intervention was negative 0.516, and the non-significant difference between both groups is 0.183. So there was a shift, but not a significant shift within that second period. And we only have 2 time points, 2020 and 2021, so not a big surprise that the results are not significant, because that's a rough period for both groups. And so we expect some changes, and they seem to have happened, but we're only looking at 2 years or 2 years within that period, so it may be more helpful to look at that summary 2. For this intervention period 2, the results show that the intervention group's significant shift in SIR post-intervention was 0.092. Control group's significant shift in SIR post-intervention was 0.237. So we see that the intervention group, their SIR was significantly going down. The control group was significantly going up, and the significant difference between both groups is negative 0.328. Okay, so summary 1 and summary 2, each value represents the change per unit of time in that period. For example, in summary 2, there is a significant difference between both groups of negative 0.328 for each year. So with it for each year, the difference grows by negative 3.28 for our intervention and control group. So again, we have a lot of variables in the segmented regression, a lot of interpretations, and maybe sometimes confusing results that may seem counterintuitive when you read the results. But so it's really helpful to look at our graphs to help understand that. We're first going to do a graph for variable importance. We do know we're seeing significant results, more so at the final period after 2022, more so than what we're seeing in 2020 and 2021 period. So let's look at the variable importance first. Okay, so I changed color to green just because we may associate a red highlighting with something bad. These variable importance plots, they don't show direction of the, they don't reflect the direction of the effect. So it's just telling us that these are significant or very important variables, and they rank them to show which are the most important. Red doesn't necessarily mean, oh, that's I'm going to get a bad finding, like things are going in the opposite direction that I'm expecting. It can't do that, but we can change the color just to show that something significant is good. And so we do that here. We change it to green just in case that helps with our audience. And we can see that the TXI and TXIP7 have the most variable importance. So let's go ahead and look at we're going to graph the model summary. And so I have my commands here for my graph, and I added in some more features so that it can help us view the results better. Okay, so I ran that code. I highlighted it and hit Control R. Okay, let me also put the variable importance up. Okay, so we can see that what happened with our data was that our US states had a decreasing trend at the baseline. Our non-US states had an increasing trend at the baseline. TXI indicates that trend, that initial baseline trend, was significant. And this is the most important predictor. So there's probably more consistency during that period. This is before 2020, before COVID. So that trend we had was probably maybe a little more consistent across our different states. And then when we look at the U.S. territories and D.C., it was increasing but not significantly. ITS time is not significant. We don't see the asterisks that would indicate the level of significance. But we do see it increasing. And I do have counterfactuals for each previous period. So we can see that, for example, if we follow this red line in the baseline, if they would have gone to that same level, if they would have continued, we would have expected their path to follow these the red dashed line. That's the counterfactual. If you look in the top left of the legend, you can see that there's a counterfactual for our U.S. non-states, and we see that in the legend. It's that dashed red line. So had our non-U.S. states maintained that same trend, we would have expected it to be about 1.3 at 2020. And for our intervention group, if they would have maintained that same trend, we would have expected it to be about at that level of 0.6 in the year 2020. But you can see something interesting happen. There was a flip where the U.S. 50 U.S. states, their trend increased, while the non-U.S. states decreased. And in 2021, they both continue to decrease and increase, respectively. And you can compare that solid blue line with the dashed blue line and the solid red line with the dashed red line. It's important to note that we only have 2 years of data, so it's hard to call it a trend just because we don't have a lot of data, and we had to what I really wanted to do was isolate that trend between 20 and 2021, and so we don't have a lot of data, but those are the 2 years that I wanted to break apart there so I can look at these. I was really most interested in the trend in 2022 onward. So, but yeah, we definitely can see something changed for all locations in the year 2020 and 2021. And so that post 5, that value represents the difference between where this that solid red line touches that gray vertical dashed line, and where that dashed red line touches that vertical line. So the difference between the two would represent that negative 0.22, and for IXP5, that would represent again a difference, the difference between the blue, where that blue line is at, where it touches 2020, and where that dashed line, the blue dashed line, where that's at. The difference between those two minus the difference between where the red and the red solid and red dashed lines touch the gray vertical line. So the difference between these two distances, the trend, or the difference in the intervention group minus the difference in the control group gives us that IXP of 0.46. So what happened is that our trend lines the trends increased for the U.S. states, but decreased for the non-U.S. states. So that gives a positive value for that IXP, meaning there was an increase for our U.S. states. And we can see that here, that clearly things changed for both groups. And so now we can go over to our our second interruption, which is at 2022. And the idea is that maybe things have improved, and now we can see improvements in our data, and we can see that we're comparing the 2022 to 2024 period with our 2020 and 2021 periods. We can see that for the most part our level stayed about the same. We can see that it's probably about I guess about maybe 5 SIR points lower for our intervention group in 2022. And then we can see there's a big change for our non-US states where it increased from about, I want to say that's about 0.75 maybe. We go across, it's somewhere around 0.75. And then where it wound up for that solid red line up top is probably about, I want to say about 1.3. Okay, so the difference between that about a 5-point decrease and the difference between, think about 0.75 and about 1.3. If you were to subtract our blue difference by our red difference, that comes out to negative 0.65. So we would have expected we could have expected a different trend for the intervention group, and instead they're just by only being a few points lower in comparison to what happened for our non-US states, that would suggest that there was an improvement for our intervention group. It's kind of hard to think of that big of an improvement when where they're at in 2021 and 2022 are not that far off. But when you take into account the difference for the control group, which would suggest what could have been for our intervention group, the difference in their trends is a lot bigger than it seems. It's when you take into account, if you cover up the red part on this graph, we probably wouldn't have expected that to be as high as it was. So what the results tell us is that our U.S. states were able to have more stable or consistent results rather than a big jump in our SIR like we saw with our control group. And so when we look at TXIP, it has a value of negative 0.51, so it's decreasing about half an SRI point per year. And that's a significant decrease as well. And if we look at TXIP, that's the second most important predictor on the far left. So we do see signs of a positive effect for the U.S. states. And you may also notice that that trend is not too, the trend that we see for both our intervention control group, the trend in the first period, the baseline, and the last period starting at 2022, we can see that it's kind of following what we might have expected if there wasn't that middle period of COVID. One's higher than the other, and they tend to increase. So if you would just kind of follow this middle counterfactual, this middle dashed red and blue line, they kind of go in the direction that we end up in after 2022. So that's helpful to know. Okay, so now we've completed those. We're gonna read through our conclusions. The trends flipped in 2020 and 2021 and then returned in 2022. DID and ITS explain the COVID effect in 2020. Only ITS explains the 2022 effects. Both approaches can help answer different questions. ITS is more helpful with more complex questions over time, but DID provides an easier interpretation in results and graphing. Number 4, ITS lets us see the most dramatic changes in 2022 compared to the main COVID years. Number 5, a simple pre and post test would suggest there was no difference before and after COVID for the U.S. states, but by adding a comparison group to help us understand what might have been, we see that maintaining a steady level in the face of great change is success. We can use the same analyses to identify false success. A pre and post test may wrongly show program success because the control group has also experienced a rapid SIR decrease if coming out of a high rate and high variation during 2020 and 2021. For example, imagine a CAUTI intervention starting in 2022. The high 2020 rates due to COVID could falsely imply a program success if the rates dramatically increase. I'm going to rerun this code just again. And so what I mean by that is if we had we often use 2 years of baseline data. So imagine we have an intervention in 2022 and we have high rates. We don't have it here, but imagine we have high rates because of COVID in the baseline period, 2020 and 2021. And then if we see a rapid decrease, say going along where this counterfactual is at, if we saw that, then it may suggest that, oh, that's great. We had a high rate back in 2020 and 2021, and now it's dropped dramatically. That might be because we did have an effect by COVID, and so that might falsely show a program success, where it may have been that years before we might have had that equally low rate. So in the very early years, we may have a low rate, then it may shoot up because of COVID in 2020 and 2021, and then come back down to its previous years, to about where it's normally at. So we might, by using the interrupted time series, we can identify that. If not, we could run into the issue with your routine t-test that the improvement that we're seeing in that last period is due to the fact that how we measured it, how we tested it, that 2020 and 2020 period might have just been a bad baseline, because it's starting out at such a high rate, anything looks like it's improved. So if you're just doing one group, it's going to look like that there was false success with your intervention. If you add in the control group and a baseline that you can use interrupted time series on, then it'll appropriately show that no, we're just basically back to where we were at before, and it wasn't our program. So we can use these methods to highlight when we do have a success, but we can also highlight when we don't have success and save our hospitals a lot of money and time by investing in programs that don't work. Okay, so now we're on to study 2. And our questions are, did COVID-19 impact CAUTIs, CLABSIs, SSIs, and VAEs in the 50 United States? And this analysis, we're just looking at these 50 United States. We're not looking at the U.S. territories. So this data would be the CAUTI, CLABSI, VAE, and SSI data sets. Another question we have is, was there an improvement in 2022? We have no control group. All 50 states experienced COVID. So this is a really big benefit of the interrupted time series, is that when we don't have an intervention group, what do? Because we're doing segments, we're comparing one segment with the other segment. So what we can do instead is do an interrupted time series. We don't need a control group. Our counterfactuals that we need to say what the program effects are based on our prior segments. So our comparison group is actually our previous period. We can answer if things have gotten back to normal, make a better comparison with 2022 using a more relevant 2020 instead of 2016. So it may be 2016 may be just a different period altogether. We want to know what happened in the face of that COVID. So what we can do is compare that 2022 onward period with the 2020 and 2021 periods. And we can see if all infections change the same way in 2020 and 2021. So we have a middle period for those 2 years. Did everything go up in 2020 and then come back down in 2021? Or was there a mix and match where for some infections they increased in 2020 while other infections had the biggest increase in 2021? We can identify that with this type of analysis. We're going to do a one-group interrupted time series. Because COVID-19 had an impact on all states, we don't have a control group. When examining just the data of the 50 U.S. states, only CLABSI had significant U.S. state versus non-state differences. And that was the analysis I did right at the beginning, so I'm not going to do the differences as well, because for these we're going to see no difference. There's only the CLABSI outcome that really where we really saw that difference between the U.S. states and the non-U.S. states. The analysis option we have with no control group is the interrupted time series. So let's begin. I'm going to highlight the code for the CLABSI model. And this, again, is all 50 states. I'm going to use the same U.S. state variable. Because I don't have any non-U.S. states, this value would be 1 for all states, for all rows of data. And we're going to look at year is our intervention time. And we're going to have interruptions at the years 2020 and 2022, and these are the 5th and 7th year of this data. For the ITS argument, I selected 1 because we only have one group. So I'll run that. Click the run icon at the top as an alternative, and I'll get a summary. And we have all of our predictors, and you can see that with almost all of our coefficients showing up as significant, that there are a lot of changes going on. We have significant shifts in the intercept, as well as significant trend changes. For these variables, we're actually going to look at post 5 and TXP5, post 7 and TXP7. I don't have the I in any of these variable names because by default there's not an intervention. We're just looking at the same group, a single group, so we don't have a true intervention, so there's not a need to indicate if it's an intervention group when we don't have I guess we don't really have a control group either. We have all. So just to make it, just for brevity, we're going to change, we're going to use the variable or coefficient names that don't have the I in it. So post 5 and TXP5 and so forth. So for these, it's probably just really easier to look at the graphs. So we're just going to do the graph for our first outcome is CLABSI, or the SIR for CLABSI. Okay, so we have that here. Title is ITS US CLABSI SIRs by year. It's a similar graph to what we looked at earlier. I changed the colors just to make it a little easier to sort these. In our legend, we have the SIR trend. I have those in the solid green lines. We have our counterfactual in the dashed green lines. We can see what could have been if there wasn't a change in 2020. And we can see a big change in the level or the intercept. Post 5 has a SIR change that increased by 0.24 points. That's very significant. So that's what post 5 represents, that shift in the level immediately starting in that first year for of this new period for 2020 and 2021. So it shifts up by 1/4 point. Our trend TXP5 also increases. That's significant as well. That's almost 1/10 point. Only 2 years there, so it only increased by that much in 2021. And now we look at the shift starting in 2022, and that's that second dashed gray vertical line. Had they continued with that that kind of trend, it's a bad thought to think of, but imagine if COVID continue to have that same effect it did in 2020 and 2021. Imagine if we saw that continue. We know the vaccine helps, so that was, and our hospitals began to treat COVID better. But imagine if they couldn't, what that trend could have looked like. That dashed line would have continued upward. Instead, we saw our CLABSI rates decrease. So that shift in our level was 0.06, but not significant. However, our change in our trend significantly decreased. So it was going up in 2020, it started going down in 2022, and that big change represented a difference of 0.12, about 1/9 point per year. And so that's very significant. And we can see that there was just a change every few years. So that was quite a difference. Okay, so now we're going to close that. We'll go to our next SIR. And that is for the CAUTI SIR. I'm going to run that. And I'm going to produce a graph for that. Okay, so we see a similar trend, a similar set of trends. We see it decreasing in the baseline. It sprang up, most notably in 2021. We see that's a significant trend. A difference. It's increased a lot. It was going down. It went up more so than it went downward in the baseline. So it has a positive value for the coefficient. TXP5 equals 0.23. It's significant. This level it's actually not in the graph, but that dash line should be going upward above the graph, probably around where that R is in year. So that's, but instead we see that the level goes down to about 0.75 or 0.72. And so the difference between the levels of where it could have been and where it was is a negative 0.39. So that shift downward. And we see the trend in the difference in the trend at TXP7 is significantly different and lower than that trend that we see with TXP5. So in that middle period, we see it going up, trending upwards. In our final period, it's trending downwards, and significantly so. Okay, so we'll close this for now. Now we're going to go to VAEs. Run the model. Now we're going to produce a graph. Okay, so during the baseline, VAEs, our ventilator-associated events, were a little more level. Just a slight decrease of 0.01 per year. That's not a bad slope. It's coming down. It's level. It's consistent. I guess we'd rather it come down at a more decreasing rate. However, we do see a big shift in 2020. It's increased by a lot, but then comes down again in 2021 to similar levels that it was in the baseline. And then when we look at 2022, we see that it increased more. The trend is, you see in that third period, we see that line coming down. So you would expect that you might expect that TXP7 has a negative value of, instead it has 0.25, and the reason why we have a positive value of 0.25 is because we're comparing the trend after 2022 versus the trend in starting in 2020. So, and the reason is that because although this trend is going downwards, it's not nearly going down as steep as what we saw in this middle period between that represents 2020 and 2021. So it's so overall it's going upwards more so in this final period than it is in this middle period. In this middle period, there's a sharp decrease. And we could have this pointing down more, and it would still show up as a positive TXP7 coefficient. And so if it would have continued at the same type of downward trend in the middle period, if it did that in in that last period, I'm not even sure what degree angle that is, but if the angle of the decrease matched, if it was the same for these last two periods, then TXP7 would have been 0. So it's just, we can clearly see it's decreasing, but in comparison to the previous period, which interrupted time series does, this trend is has a positive trend compared to what we see in the middle period. It's just that middle period has such a steep decrease. But that's really helpful to know that, because this trend has shifted. It's leveling out. The actual level or the intercept has increased, so I'm going to say level there. But in terms of how even it is, it's evening out in these last 3 years. So that might be surprising. So maybe I'm trying to think how things were in 2022. Maybe COVID had an impact on ventilators or ventilator associated events, and that may be part of it as well. But I think with the steady baseline, it's surprising not to see that. Although it does have kind of a steady trend in the last 3 years, it feels odd to not see this level down lower. So it feels like something else is going on here. The general trend in the baseline period and the post-2022 period are somewhat close, but the intercept is a lot higher than where I would have expected it to be at, based on that drop off. Okay, so let's close this up for now. And we're doing the SSI, the colon procedures, and we're producing the graph. Okay, so we see something similar again with our other graphs. We see a baseline that was improving before 2020. We see it actually continue to drop, and more so than expected in 2020, and then come back up again in 2021. In my hospital system, we actually had fewer procedures in 2020. So there were fewer surgeries. I think we may have even seen a lower SSI rate. But that might be if it was similar across different hospitals in the U.S. If hospitals were performing fewer procedures in 2020, that may have something to do with it. That may be why we got our SSIs down. So it may have been natural that they sprang up in 2021. That's kind of high. So when we look in that final period, we see that the intercept dropped, and it's going up actually at a significant rate. Well, maybe compared to 2022, it's kind of flat, but when you compare, we actually have the opposite happen here that we saw with VAEs. In the middle period, we see an increasing, almost skyrocketing increase for that middle period. We see it jump up a lot by 2021, which shows an increase. Again, we're only looking at 2 years in this period, so it's kind of hard to make to say that there are big implications from that. But in that middle period, we do see an increasing rate, and we see an increasing rate between 2022 and 2024. However, we do get a coefficient values that's negative 0.15. TXP7 equals negative 0.15. So it may seem odd to actually see an upward trend with a negative coefficient, and the reason is that in comparison between this third and final period with what was going on in 2020 and 2021, we're seeing a drop off in that trend from the middle and period on the right. So that's why we have a negative value. It's although it is increasing, it's not as nearly of a steep rate that we saw in 2020 and 2021. So again, had this slope been the same in this third period as it is in the middle period, if whatever the angle that is of an increase, almost looks like a 60-degree angle, versus like a 20 or 25-degree angle. Had we seen 60-degree angles in both period, then TXP7 would have equaled 0 because it's a much less steep increase. That gives us a negative value for TXP7, and it's a significant change in trends. Okay, so now we've gone through all 4. I'm just going to go down, create this final graph which has all 4 together. Okay, so now we can see what the changes look like for each of our infections, the SIR rate, and the one that may have been impacted the least, that kind of sprang back to its original trend. It's probably CAUTI on the top right. You can see in that baseline period there's a trend going down. We follow that dashed pink line in the middle, and it's not too far off. If we were to continue that, it's not too far off what we see on the right side. That trend, it's going about the same angle. It's almost at that same intercept or level, but not quite. But still, that's not too far off. The biggest difference we probably see is on the bottom left with VAEs. The type of trend we get in the first and third periods are similar, but they're at different levels. The SIR is higher than we would have expected had they continued that same trend. So I think there was some impact there, but I don't know exactly what it was. So let's go over to our conclusions. We see things look differently in SIRs during 2020 and 2021. For some infections, SIRs seem to be back on track, like CAUTIs, while others need more time, like VAEs. We see which things are most susceptible to change, and maybe some insight into the potential impact of seasonality in general terms. Maybe some things might be impacted by winter months versus summer months. Maybe CAUTIs might bounce back and forth, but fall back into a predictable pattern once that effect of seasonality is gone. Maybe not. There might be some other differences we can spot there. But overall, we do see an impact with COVID. And if you're running these programs, you should keep in mind what the effect was on and this goes for any of our outcomes, such as HAPIs, readmissions, maybe even mortality rates, length of stay. If there's been an impact with COVID, we would want to rule that out. These causal models help us do that. They can help identify when we've had success. For example, we may see that we had an impact. If we go back to our CLABSI example, we saw that although we had what looked like a level trend with our differences, we can see that it could have been a lot worse if we compare it with our control group, where their SIRs just jumped up quite a bit, although ours remained even. We had a flat trend. We can say that consistency is victory in itself. But we can also use these causal models to show that, we're seeing a lot of trends just dropping off in the middle periods. For example, VAE, and not really with infections as much, but other types of stay I've seen where we have this steep drop off in 2020 and 2021, and then it may suggest that we had a big improvement in 2022, but we may, because we did a pre and post test, and it's sort of like running downhill. As you go down, as you run down, your speed picks up, and it looks different than at a flat surface where things are normal and consistent. But if you're starting from a high point, it may be just natural to see rapid success just coming if you're using that higher point as a comparison. So there's a lot of benefits to these causal models. They help highlight success. They prevent us from seeing false success, and they provide a lot of information. So when you have the opportunity for a control group, or even if you don't have a control group, you can use these types of models to help understand that trend, especially if there's something that has impacted that trend over time. So thank you for watching this, and I hope this can be helpful to your work. Thank you.